Hmm. If you're wondering what to get old Dr. Cook for Christmas, Dot Cam, top of the list. New Dot Cam for your boy would be amazing because this one he is like constantly moving slightly. See how it's like slightly moving right now? You see how the duct tape is starting to come into frame? This is the life of this camera. Okay, we don't care about the dot cam. We hear Dr. Cook complain about the dot cam all the time, and we don't really care. So let's let's talk about the homework key. 39 wants us. This is homework. The first homework from chapter 6. Question 39 wants us to draw arrows, I believe. Give the reactions and products. Given the reactions and products, supply the missing curved arrows and add the electron pairs as needed. So, well, this one really has an alone pair on this carbon. That's why it has a negative charge. Okay. And this is going to be really basic. We know that the pKa of an alkane carbon is like super high. It's like 50, 10 to the 50 is the Ka. So, or 10 to the minus 50, excuse me, is the Ka. So it's basically not an acid at all. It means its conjugate base is going to be extremely strong. Okay. So we're going to draw from the lone pair to this H. I need to fully draw out my water so I can show that this lone pair that was holding that H now goes onto the oxygen. So that leaves me with an oxygen with 3 lone pairs then and a minus charge. Right? That's my arrow pushing for that one. Okay, next one. This is going to be my base, right? We can see from the already written out reaction that this is my base. It's gained the proton. And it took this proton off of the nitrogen. And again, I need to actually show that N to H bond in order to do the mechanism correctly here. So now I ended up with a lone pair on my nitrogen, right? And an H now on that alcoholate group or alkoxide group, right? That's what this is called. I now have an H stuck on there as well. Okay, and I showed that on my mechanism. Okay, next one, I'm removing one of these protons, so I need to redraw this to actually show one of the proton I'm going to take off. And this nitrogen has a minus charge, means it has 2 lone pairs. So one of those lone pairs is going to scoop up this H, and it's going to kick its electrons back down to the carbon. All right, so that puts a negative charge on this carbon, which means it must have a lone pair. It's a carbanion. And then this nitrogen still has the other lone pair, right? It started with 2. It used one of them to accept that H. Okay, then this one, I'm putting an H, so I need to redraw this in this way so I can show where the electrons are going. I'm putting an H onto this carbonyl carbon, or this ketone, or not the carbonyl carbon, but the oxygen of my ketone here. So this lone pair is going to attack this proton. The electrons that we're holding are going to kick off to the oxygen now. So I'm going to get regular old water, and this oxygen is only going to have 1 lone pair, right? Because it used its other lone pair to accept that proton. Okay, there's my arrow pushings. Those weren't too bad. Now for the good stuff. 50 and 51, which are ranking acidities of things, if I'm not mistaken. First one wants to know what's the most acidic proton and estimate its pKa. Well, if we know our pKa is from the textbook, this isn't too difficult. So what are all the possible protons I could have on this first molecule? I have an alkene, that's like pKa 45, so not acidic at all. This is like 45. This one's like pKa of about 50, right? Because it's an alkane, the CH3. So 45, 50. This alcohol is about 16, right? That's our ballpark for alcohols. This one is a special type of alcohol. So it's an alcohol where the conjugate base can be resonance stabilized by this benzene ring. All right. So if I remove this proton, I have this minus charge that I can actually draw resonance structures through this ring with. This is called a phenol. We talked about this idea of phenol earlier in the semester. Phenols have a pKa of about 10. It's not one you have to memorize, but you should have been able to find it on the chart that's in the book. Okay, they're more acidic than the other alcohols by, a significant margin. Right, 10 to the minus 16 versus, or sorry, 10 to the minus 10 versus 10 to the minus 16 for this H falling off. So this is my most acidic proton here. Okay, next one, what are my possibilities? I have a ketone proton here. I have an amine proton, and this is talking about this is most similar to this reaction, NH3 going to NH2 minus, right? So don't get confused and use the wrong pKa for your amine on this group. Okay, so carbonyl hydrogen, I have an alkane hydrogen down here. So we said this is about 50 for my alkane hydrogen. Ketone hydrogen is about 20. That's one we have to know. And amine is about 38, right? If we're going to form NH2 minus, or in this case, it would be NRH, excuse me, no, that was right, NRH minus would be what we'd have. If we lose one of these H's, we leave behind a negative charge, so it's basically swapping one of these for the rest of the molecule here, swapping one of these H's, if we're trying to just compare it to what's in the book. So the most acidic one then is going to be this one, right, the ketone one, because it has the lowest pKa. Okay, next comparison, we have a carboxylic acid, which is about 4. We have alkane, which I hope we're starting to realize can be disregarded in most of these conversations, right? Alkane proton is just so weakly acidic that we're not really going to get much of anything, right? So this one would be about 50. This is a ketone hydrogen, that would be about 20. And then this is a thiolate, or sorry, not a thiolate, but a thiol, so a sulfur a version of an alcohol. It's going to be roughly in the ballpark of an alcohol, is what I'll say for now. I guess really sulfur is less electronegative than oxygen is, which means it's going to be a little bit weaker of an acid, but for now we can just ballpark it at 16 because it's unlikely to reach as low as the pKa of my carboxylic acid, which is going to be my most acidic proton here. Okay, so remember, a molecule doesn't itself have a pKa unless it only has one acidic or basic site. Okay, each site in the molecule, each hydrogen is going to have its own respective pKa, or each acidic or basic site. We could consider, if we have basic sites, we can consider the pKa of the conjugate acid. Okay, so this stuff is all really confusing if you don't get the vocabulary down. It's something that requires some practice and thinking about. Okay, next one, we have an amine. This is like 38. I have some alkanes, right? This hydrogen, this would be about 50. So none of those are going to be relevant. This one that's next to the C triple bond N. So I really don't like that the solutions manual compared this to an alkyne, because an alkyne proton is actually coming off of the multiply bonded sp carbon. In our nitrile that we have on this problem, we're not looking at the hydrogen that's on the nitrile group or the cyano group. We're looking at the hydrogen that's on the carbon next to it. So this is still an sp3 carbon that we're looking at, right? And it's attached to other stuff too. I'm looking at this carbon to hydrogen bond. So that's really closer, if you ask me. That looks more like a ketone, right? It's the carbon that's adjacent to the C double bond O that we're looking at for a ketone. Right, the hydrogen on the carbon adjacent to the C double bond O. Here we're looking at a hydrogen on a carbon adjacent to a C triple bond N. So I would put the ballpark for nitrile more like 20 here. They called it 25 in the book, which was more like an alkyne, but that doesn't really make sense, right? That would make sense if we had an H that was attached to the carbon that was triple bonded to the N, but we don't. We have an H attached to an sp3 carbon, so this is more like a ketone. So 20 means this is my most acidic proton, and its pK is about 20. Okay, this one, I have an alcohol, or this is actually a phenol, right, which we know now is about 10. And then over here, I have something that looks sort of similar to sulfuric acid. So it's like negative something. I don't even really care exactly what it is because I know it's just negative, and I know that this is positive. So this is definitely going to be my strongest proton to leave. I also have an alkene here if we wanted to say, don't you have an alkene there? Well, you're right, I do. Okay, this one, thinking about our pKa values again, for a protonated amine with a positive charge, our pKa is about 9 or 10. Then alkyl, right, this is going to be about 50. This is a ketone, it's going to be about 20, ketone hydrogen. And then this is an amide, so we don't know the value of an amide hydrogen, and it might be in the book. I'm not sure if it's in the chart that's in the book or not. But let's just call it like an amine for now. If we compared this to say that this was like an amine, we know that it would be up in like the 30s or something, right? It'd be like 38 for just a regular amine. For an amide, this is going to stabilize the conjugate base, which is going to make it more acidic. So I believe for an amide, the range is about 16. It's not one you have to have memorized. But in any case, you can just compare the charges on these, right? I have an uncharged nitrogen versus a charged nitrogen, and I know that these are out of the running already just by pKa. So even if I don't know this pKa, I can use that carry, right? Charge, atom, resonance, induction. The charge is different on these two nitrogens. So the positive charge one's going to be more acidic, and it's going to be about 9. Okay, last one. What all do we have? We have an alkyl. We have an amine, which we said amine losing a proton is about 38. Alkyl is about 50. We have an alpha to an alkyne, right? This is probably more along the lines of 20-ish. It's probably actually not quite 20, maybe more like 25. Well, sorry, that's not even what we want to be talking about right now. We want to talk about the alkyne proton. The one that's adjacent to the alkyne is going to be a little bit more acidic than like the one that's all the way down here, because this is kind of an electron withdrawing. The alkyne's very electron deficient. They have 2 carbons sharing 6 electrons, so they're not real happy. They're going to kind of pull electrons towards themselves. So anyway, this one's going to be more acidic than this one for sure, but not more acidic than one that's on the sp3 on the sp carbon, right? This is a sp carbon. This is a sp3 carbon. This one, we know alkyne is about 25 for our pKa, so this is going to be the most acidic. This one, I don't know, it's maybe more like 30-ish or something, because this is less electron deficient than a carbonyl. Okay, moving on. 51, we want to know what is the most basic site in these molecules. So I could think about that as which one has the weakest conjugate acid, right? I could think about that. I could think about this in terms of drawing out my conjugate acids, and that would be a good way to think about it too. So the conjugate acid of this would be like this, right? The conjugate acid of this one, if you'll allow me to just fragment the molecule here to prevent redrawing things, conjugate acid of this one looks like this. The chain in the middle is not, okay, let's just redraw it. What it takes what, 3 seconds to redraw it and 5 seconds to talk about it and complain about it. Let's just do it. Okay, so here's my conjugate acid. I want to think which one of these is a stronger acid. Well, I know the pKa of this is about 9, and I know the pKa of this alcohol is about 16. So this is the stronger acid, which means it's more stable as the conjugate base, right? Which means that this must be my more basic site in this molecule, is where I have the less stable or the less acidic, right? The less acidic conjugate acid, the weaker conjugate acid gives me a stronger conjugate base or stronger base. Okay, next one. Now I'm looking at essentially thinking about what if this was an OH2, what if this was an NH3 plus, then could I use my pKa values that I know already to think about this? Well, I said this one's about 9 for protonated amine. This one is about minus 1.7 or minus, maybe more like minus 1. Okay, because this is kind of analogous to H3O plus. I've just swapped out, let's write this over here. This is kind of analogous to H3O plus, this group. I've just swapped out one of the H's for this carbon fragment. Okay, so H3O plus we know is minus 1.7, so this is also about minus 1.7. So this is going to be a really crappy base, right? This is a super strong acid. The conjugate acid is really strong, so this is a terrible base. This is going to be our better base. Okay, next one. So here I have a negatively charged sulfur versus a neutral oxygen. If I go back to the pKa's of their conjugates, this one's going to be around -1 or -2. I'll just call it -1 for this. This one's going to be around -1, right? It'll be a little bit less acidic than H3O+, because it has the electron donating groups attached to it, the alkyls. This will be about -1, and we said this is more like an alcohol. We call that about 16 for its conjugate acid here. So this is the stronger acid, which means this is the less basic site. This must be the more basic site, because this is a really weak acid. Okay, here I'm looking at a carbon versus an oxygen. So now we want to think about which one of these has a more stable negative charge. A minus charge is more stable on a more electronegative element, which would be oxygen in this case. So that's not going to be the stronger base, that'd be the weaker base. This is the stronger base, right? The charge is less stable, which makes it a stronger base. It wants to accept an H plus to get rid of that minus charge and become more stable. And then this one, it's the same argument, right? Negative charge is more stable on a more electronegative element. So this one's less stable, more reactive, stronger base. Okay, so that's it for this homework. Come talk to me, send me an email if you got questions, and I hope that you guys are enjoying these videos or that they're helpful in some way. Okay, let me know how else I can be of help.